Right now, thousands of meters beneath the surface of the Pacific Ocean, something is moving. You cannot see it. You cannot feel it. Most people on Earth have no idea it is happening, but climate scientists are watching it with a level of urgency they rarely show in public. It is a wave, not the kind that breaks on a beach, not the kind that surfers ride. This is something entirely different. An enormous pulse of warm water, stretching thousands of kilometers beneath the ocean surface, racing eastward across the Pacific at the speed of a slow river. Scientists call it a Kelvin wave, and in the spring of 2026, they detected one of the largest ever recorded. What that wave carries with it, the heat building in its depths, the energy it is transporting toward the coasts of South America, is the early signature of something the world has not seen in nearly 150 years. A Super El Niño. Not a strong El Niño, not an unusual El Niño. A Super El Niño, the kind that, the last time it appeared in full force, killed more than 50 million people. That was 1877. And, as of June 2026, the European Center for Medium-Range Weather Forecasts has issued something that rarely appears in climate science. A 100% probability, not 80%, not 90%, 100% probability that a Super El Niño will develop by November 2026. This is the story of what that means, what it has done before, what it is about to do again, and why, this time, the world it is arriving into makes everything more dangerous than it has ever been. Before we can understand what is coming, we need to understand what El Niño actually is, because most people have heard the name. Very few understand what it does. Start with the Pacific Ocean. It is not just large. It is almost incomprehensibly vast. It covers more than 30% of Earth's entire surface. It contains more water than all the land on the planet combined. And across its enormous equatorial expanse, something remarkable happens every few years that changes the weather for every person alive. Under normal conditions, what scientists call La Niña conditions, the trade winds blow steadily westward across the equatorial Pacific. These winds push warm surface water toward Asia and Australia. They pile it up in the western Pacific, where the ocean's surface can be almost half a meter higher than in the east. Meanwhile, on the eastern side, off the coast of Peru and Ecuador, cold, nutrient-rich water rises from the deep to replace what the winds have pushed away. This is the baseline. This is what normal looks like. El Niño is what happens when that system breaks down. When the trade winds weaken, sometimes dramatically, the warm water that was piled up in the west begins to slosh back eastward. Like water in a tilted bathtub suddenly leveled, that enormous mass of warm water surges across the Pacific, raising sea surface temperatures in the central and eastern equatorial Pacific by anything from half a degree to several degrees above normal. And when those temperatures rise, the atmosphere above them responds. The warm ocean heats the air. The heated air rises. That rising air draws in moisture from across the tropics and pushes it outward into the atmosphere in completely different patterns than normal. Rainfall systems that should be over one part of the world suddenly appear somewhere else. Drought arrives in places that depend on rain. Floods devastate regions that were dry. Hurricanes form in waters where they rarely appear. And temperatures spike, not just over the ocean, but eventually over the entire planet. A moderate El Niño shifts weather patterns, disrupts harvests, raises global temperatures by fractions of a degree. A strong El Niño does all of that, and then some. A Super El Niño reshapes the world. The technical threshold for a Super El Niño is precise. Sea surface temperatures in the central equatorial Pacific, specifically the ENSO 3.4 monitoring region, must rise to 2 degrees Celsius above long-term averages and sustain that level, not briefly, for months. That threshold has been crossed only 5 times in recorded history: 1877, 1982, 1997, 2015, and now, according to every major forecasting institution on Earth, 2026. But here's what separates 2026 from every single event that came before it. The latest ECMWF ensemble models are not forecasting a peak of plus 2 degrees. They are forecasting a potential peak of plus 4.5 degrees above average in the Eastern Pacific regions. The 1997 to 1998 event, widely considered the most destructive Super El Niño of the modern era, peaked at plus 2.4 degrees. What the models are projecting for late 2026 would be nearly double that. NOAA's Climate Prediction Center has assigned an 82% probability that El Niño emerges between May and July 2026, and a 96% probability that it continues through the Northern Hemisphere winter of 2026 into 2027. Wilfran Mufuma Okia, Chief of Climate Prediction at the World Meteorological Organization, stated publicly in May 2026 that climate models are now strongly aligned and that there is high confidence in the onset, followed by further intensification in the months ahead. This is not a fringe prediction. This is the consensus of every major climate modeling center on the planet. The question is no longer whether it is coming. The question is how large it will be when it arrives. To understand what a Super El Niño at this scale could mean, we need to go back, way back, to the year 1877. In the spring of that year, something was quietly going wrong in the Pacific. The trade winds slackened. The warm water began its eastward journey. The ocean temperatures climbed. Nobody understood what was happening. The science of El Niño would not even be named for another 50 years. But the consequences were already being written across India, across China, across Brazil, across Africa. In the language of drought, the monsoon failed over India. In a country of hundreds of millions of people, where the monsoon was not a weather event, but the entire foundation of food production, the rains did not come. By 1877, the failure was catastrophic. In the Deccan Plateau, one of the most agriculturally vital regions of the subcontinent, crops failed across an area of 670,000 square kilometers. 58.5 million people face starvation. Excess deaths have been estimated at between 5.6 and 9.6 million in India alone. Florence Nightingale, witnessing reports from India in 1877, wrote, "The more one hears about this famine, the more one feels that such a hideous record of human suffering and destruction the world has never seen before." She had not yet seen China. In the northern Chinese provinces of Shaanxi, Zhili, Henan, and Shandong, the drought arrived with equal ferocity. Rivers ran dry. Harvests vanished. Government relief was inadequate and delayed. Between 9.5 and 13 million people died in China alone. A missionary named Timothy Richard journeyed to Shaanxi province in early 1878. His famine diary described conditions so extreme that the words feel impossible. He wrote of people pulling down their own houses for fuel, selling their children, eating roots and clay, of bodies on roadsides, of hunger so total that the social fabric of entire regions simply dissolved. In Brazil, the Grande Seca, or the Great Drought, destroyed the agricultural Northeast. Hundreds of thousands died. Millions were displaced. The economic damage echoed for generations. The death toll across all affected regions, India, China, Brazil, Africa, and elsewhere, exceeded 50 million people. That represented 3 to 4% of the entire global population at the time. Researchers who have studied this event have written, "It was arguably the worst environmental disaster to ever befall humanity, and it was triggered by ocean temperatures in the Pacific rising, approximately 2.8 degrees Celsius above normal. The current forecast for 2026 suggests temperatures of 4.5 degrees. But perhaps you are thinking, that was 1877. The world is different now. We have technology. We have early warning systems. We have global food supply chains. That is true. And it matters. But there is something else that is also true. Something that makes 2026 fundamentally more dangerous than any previous Super El Niño in the modern era. The planet arriving into this event is not the same planet that faced the last one. It is warmer. The baseline global temperature in 2026 is approximately 1.3 degrees Celsius above the pre-industrial average. That means every El Niño event now sits on top of a planet that is already running a fever. The additional heat El Niño injects into the atmosphere does not add up from zero. It adds up from a starting point that is already elevated. During the 2023 to 2024 El Niño, a moderate event, nowhere near Super El Niño strength, global average temperatures briefly crossed 1.5 degrees Celsius above pre-industrial levels for the first time in recorded history. It triggered the hottest year ever measured, the fourth global coral bleaching event on record, unprecedented wildfires across multiple continents simultaneously. That was a moderate El Niño. What is coming in 2026 is categorically stronger. And the systems it will strike, the ecosystems, the food networks, the infrastructure, are already weakened. They have not recovered. This is what separates 2026 from 1997, from 2015, from every event before it. It is not just El Niño arriving. It is El Niño arriving on top of everything else that has already happened. Let us talk about what a Super El Niño at this scale actually does to the world. Not in abstract terms, in specific, measurable, documented consequences. Starting with the ocean, the world's coral reefs, among the most biologically diverse ecosystems on the planet, covering less than 1% of the ocean floor, but supporting roughly 25% of all marine species, are in a state that makes scientists deeply afraid of what is coming. The 2023 to 2025 global coral bleaching event, the fourth mass bleaching on record, affected reef systems in at least 82 countries. By April 2025, 84% of all monitored reef structures had been exposed to bleach-level heat stress. Bleaching occurs when ocean temperatures rise just 1 degree Celsius above the monthly maximum and remain elevated long enough to force corals to expel the algae living inside them. Those algae are their primary food source. Without them, corals begin to starve. During the 1997 to 1998 Super El Niño, approximately 16% of the world's coral reefs died in a single year. That was a global temperature anomaly of plus 2.4 degrees. The reefs entering 2026 have not recovered from the bleaching events of 2023, 2024, or 2025. Recovery from severe bleaching requires 10 to 15 years for slow-growing structural corals. The intervals between bleaching events are now shorter than the minimum recovery window. These reefs contribute approximately $2.7 trillion annually to the global economy. Through fisheries, coastal protection, and tourism, hundreds of millions of people depend on reef fisheries for their primary protein source. They are going into a Super El Niño, already critically damaged. The food consequences extend far beyond coral reefs. El Niño events are estimated to affect crop yields on at least a quarter of global croplands. The mechanisms are specific and well documented. In Southeast Asia, the world's largest rice-producing region, El Niño brings drought. The monsoons that water the rice paddies of Indonesia, the Philippines, Vietnam, and Thailand weaken or shift. In severe El Niño years, harvests collapse by 20 to 40%. Rice feeds more than 3 billion people in sub-Saharan Africa. El Niño disrupts the rainfall patterns that support maize production across southern and eastern regions. Kenya, Tanzania, Zimbabwe, Mozambique, countries where food security is already fragile, face drought conditions that can push entire populations toward famine. In South America, the anchovy fishery off the coast of Peru, one of the most productive fisheries in the world, which feeds the global fish meal industry and indirectly supports aquaculture and poultry production everywhere, collapses during El Niño events. Peru's anchovy catch fell by more than 50% during 1997 to 1998. The 2015 to 2016 Super El Niño produced a near-identical collapse. El Niño conditions were already detectable in subsurface Pacific temperature readings as of May 2026. And layered on top of all of this, in 2026, is something that previous El Niño events did not face. A global supply chain already under stress from geopolitical disruption, rising energy costs, and conflict-induced trade restrictions that have driven trans-Pacific container rates 40% above pre-crisis levels. UBS chief economist Paul Donovan wrote in March 2026, "Higher fertilizer prices may not be the biggest agricultural price threat this year. 2026 might produce a Super El Niño. In that case, drought and limited water supply might be more important than shortages of nitrogen. The convergence of simultaneous failure modes is what separates 2026 from an ordinary severe weather year." Now consider what El Niño does to weather. Not in vulnerable tropical regions, but in places that consider themselves insulated from these events, because nobody is insulated. In North America, a strong El Niño reshapes the jet stream, the high-altitude river of wind that steers weather systems across the continent. The southern United States becomes wetter. The northern tier becomes warmer. The Pacific Northwest experiences heavy rainfall. California, which suffered multi-year droughts under La Niña, swings toward flooding. During Super El Niño events, these patterns intensify to extremes. The winter of 1997 to 1998 brought ice storms, flooding, and record precipitation across vast stretches of North America. Economic damage from weather events tied to that El Niño has been estimated at between $32 and $96 billion. NOAA's 2026 seasonal outlook projects above average temperatures across most of the United States and above average precipitation along the East Coast and southwestern regions for June through August 2026. The winter of 2026 to 2027, when the Super El Niño is forecast to be at or near its peak, will likely bring conditions unlike anything in recent memory. In Europe, El Niño's direct effects are more diffuse, but the indirect consequences, operating through shifted jet streams and altered pressure systems across the North Atlantic, can be significant. Warmer, wetter winters in northwestern Europe, drought conditions across the Mediterranean, disrupted snowpack in the Alps. In Australia, the link is among the most direct in the world. El Niño means drought. It means fire. During strong El Niño years, the risk of catastrophic bushfire seasons rises dramatically, as Australia experienced in the Black Summer of 2019 to 2020, when fires burned across 18 million hectares and smoke plumes circled the globe. A Super El Niño arriving in the southern hemisphere, spring of 2026, arrives exactly at the beginning of Australian fire season. Beneath the surface of all these specific consequences lies something that scientists are increasingly focused on: the question of feedback. El Niño does not just respond to climate change, it interacts with it. A warmer baseline ocean means El Niño events start from a higher temperature. They inject more heat into the atmosphere. They push global temperatures further above the pre-industrial baseline, potentially triggering thresholds and tipping points in Earth's climate systems that, below those thresholds, would remain stable. The Amazon rainforest, which stores an estimated 150 to 200 billion tons of carbon in its trees and soils, becomes a net carbon emitter during strong El Niño years. The drought and heat that El Niño brings to the Amazon causes trees to die, to burn, and to release their stored carbon into the atmosphere. During the 2015 to 2016 Super El Niño, the Amazon switched from a carbon sink to a carbon source for the first time since measurements began. That additional carbon in the atmosphere contributes to further warming, which raises the baseline for the next El Niño, which causes more drought, which kills more trees, which releases more carbon. This is not a future scenario. This is already measurable, already documented, already underway. What 2026 adds to this cycle is a Super El Niño of potentially record-breaking intensity, arriving at a moment when the Amazon is already under pressure from deforestation, when the baseline ocean temperature is already elevated, and when the cumulative carbon load in the atmosphere is higher than at any point in at least 3 million years of Earth's history. The interaction between all of these factors is not fully modeled. The feedback pathways are not fully understood. What is understood is that each of them amplifies the others. There is a question worth asking here. If this is coming, and the data says it is, why is it not the only thing anyone is talking about? Part of the answer is that climate events operate on timescales that do not fit neatly into news cycles. A hurricane forms in days and destroys in hours. A Super El Niño builds over months, unfolds over a year, and its consequences trail for years afterward. The urgency is real, but it is diffuse. It does not arrive in a single concentrated moment that demands attention. Part of the answer is uncertainty. Scientists have been careful, appropriately careful, to note that while the probability is now very high, the exact peak intensity is still uncertain. NOAA's National Weather Service, in its June 2026 discussion, noted that the strongest El Niño events in the historical record are characterized by significant ocean atmosphere coupling through the summer. And it remains to be seen whether this occurs in 2026. That uncertainty is honest. It is scientifically responsible. But it also means that the worst-case scenarios, the ones that look most like 1877, are not being stated loudly. They are being discussed in modeling papers, in risk assessments, in the private communications of researchers who watch the Pacific data every day. The Kelvin wave detected in early 2026 has been described by analysts at Severe Weather Europe as a turning point for summer and potentially the remainder of this year. The subsurface heat pulse building beneath the Pacific is being called by the same analysts a release valve. Energy accumulated over months that will surge to the surface and reorganize global weather patterns, beginning in the tropics and expanding outward. It is already rising. So what does all of this mean for the billions of people who will live through the next 18 months? The honest answer is, it depends on how strong the peak is. A strong El Niño, plus 1.5 to 2 degrees, produces the kinds of consequences that have been documented before. Disrupted harvests in vulnerable regions, elevated wildfire risk, a historically warm global year, significant economic damage, recoverable, ultimately, though painful. A Super El Niño at plus 3 degrees or above, in a world already warmer than at any point in human civilization, enters territory where the historical record offers limited guidance. The 1997 to 1998 event at plus 2.4 degrees killed an estimated 23,000 people directly in weather events and contributed to economic losses of up to $96 billion. That is the best modern analog. But the 1997 event did not arrive on top of a planet that was already 1.3 degrees above pre-industrial temperatures. It did not arrive following back-to-back years of coral bleaching that had damaged 84% of monitored reef structures. It did not arrive in a world where the Amazon was already under pressure, where global food supply chains were already strained, where the baseline for every extreme event was already elevated. A Super El Niño in 2026 is not the same event as a Super El Niño in 1997. The physics are the same. The world is not. There is something that has always fascinated and unsettled climate scientists about El Niño. It is entirely natural. It has happened for as long as the Pacific Ocean has existed in its current configuration, for millions of years, cycling back and forth, shaping rainfall and drought and temperature across the globe long before any human being existed to notice it. It is not caused by climate change. It is not a symptom of industrial activity. It is a feature of the planet's basic operating system, a pendulum that swings regardless of what we do. And yet, what we have done to the planet is changing what El Niño becomes. Not its mechanism, not its cause, but its consequences. A Super El Niño on a planet 1 degree warmer is categorically different from a Super El Niño on a cooler planet. The same ocean temperature anomaly, combined with a higher baseline, pushes the system further from equilibrium, triggers thresholds that, at lower baselines, would not be crossed, turns survivable weather extremes into unsurvivable ones. This is what makes the intersection of natural climate variability and human-caused warming so dangerous and so difficult to communicate. It is not that El Niño is new. It is that the world it is arriving into is. The 1877 El Niño killed 50 million people on a planet with a fraction of today's population, but with food systems that were far more locally fragile, far less interconnected, and far less capable of mobilizing global relief. The 2026 El Niño is arriving on a planet with 8 billion people, deeply interconnected food supply chains that can transmit regional shocks globally in weeks, ocean ecosystems already at or beyond their thermal tolerance limits, and a baseline temperature that amplifies every anomaly. Which of these worlds is more vulnerable? That is not a question with an easy answer. What is clear is that the next 18 months will be unlike any period in living memory. The Kelvin wave is rising. The models are aligned. The heat is building beneath the surface of the Pacific. And somewhere in the depths of the ocean, the most powerful climate event in 150 years is gathering itself to break upon the surface of a world that is not ready for it. There is something quietly profound about standing at this particular moment in time. We know what is coming, not because we are guessing, because we are watching it happen in real time, with sensors and satellites and models that 1877 could not have imagined. We have seen what a Super El Niño does. We have the records, we have the data, we have the history written in famine registers and missionary diaries and tree rings and ice cores. We know. And that knowledge, that precise, hard-won, scientifically grounded knowledge, is both our greatest advantage over every previous generation that faced this and somehow still not quite enough to make us feel ready. Because knowing an event is coming and being prepared for its full consequences are two very different things. The ocean does not wait for preparation. It does not pause for infrastructure upgrades or supply chain resilience or diplomatic agreements on food reserves. It moves on its own timescale. Ancient, vast, indifferent to our readiness. The Kelvin wave that scientists detected in March 2026 is still moving east as you watch this. The heat it carries is still rising toward the surface. The atmosphere above the Pacific is already beginning to respond. What happens next will unfold over the coming months and years. Some of it will be worse than the models predict. Some of it, perhaps, will be less severe. The uncertainty is real, and it matters, and scientists are right to name it. But the uncertainty cuts both ways, and the direction the data is pointing is not toward relief. This is Terrum. We will be watching. And so should you.